So good evening, everybody, again, and to introduce Iain Davis, who will tell us about operations at the CWind Pioneer. So over to you, Iain. I will stop my sharing and allow you to start.
Right. Okay, thank you. Just give us a few seconds there, gents, and we'll be there. Slideshow. Okay. Well, first of all, thank you for the invite to ask me to speak about CWind Pioneer and operating in the offshore wind farm within Northern Europe. Got a short presentation. It's split into three distinct areas. First part, I would just like to give you a bit of background to CWind company and how it's developed over the last 13, 14 years. The second part will be some of the details about the vessel itself. And then the third part is actual how we conduct operations in the offshore wind farm as far as crew transfer vessels are concerned. And then a period at the end. If there's any questions, then please fire away at the end of the presentation. So apologise that the PowerPoint, the slides, I haven't put any development in them. It's just a slide will come up with a number of bullet points on it. I haven't developed it any way. I haven't made it overcomplicated. So let's get it started. And the first thing I really want to do is give you the history of CWind. Very small company. And as you see, 2010, they formed the company, and it was quite unique in the crew transfer vessel operation. And as much as it offered shared boat ownership, 50% funded by the owner stroke skipper and 50% owned and managed by CWind. And it was a relatively quick start with 4 or 5 boats initially. And by 2014, we had approximately 10 CTVs, crew transfer vessels, operating.
Excuse me, Iain, just for a moment, because I think I had the wrong option on sharing. So if you could try resharing your presentation.
Let me minimize this then. So if I minimize, where am I going? Back to the Zoom?
Well, back to the share screen option again and see if you can repress it.
Oh, that one now. Boom.
I'm not sure where to start. How do you feel about rescuing? Rescue tickets and bring them here and they can enjoy time with us. I'm going to ring my friend Susie.
Okay, right.
Is that better? That looks better.
That's working very well, thank you.
Right, that looks better. Okay, let me just try and get under there then. Can I get under that? Okay, so I don't know if you heard anything or... Yeah, I think you probably heard everything I'd said, but just didn't
yes.
see
Yeah.
it was on the screen.
No, that's right.
Okay, yeah, so what I was saying, yeah, so it was a unique business, 50% owner skipper and 50% CWind, and CWind managed and got the contracts, and the actual day-to-day running was done by the skipper stroke owner. Quite a unique operation, and it had its difficulties. You can imagine a vessel came out of contract. If there was 3 or 4 vessels waiting that didn't have a contract, what vessel would get it? You know, so that it was it was quite a difficult period for the company. The vessels. Hello, sorry, I'm hearing somebody there in the background.
Could I ask everybody to mute for the moment to allow Iain to talk?
Okay, thank you. The vessels that we were using at that time were a company called Sea Truck. They were GRP catamarans, all within the 19 to 22 meter length. Various hull designs, various propulsion methods, from water jets to controllable pitch props to normal props. And as I said, different hull designs. There was some swath catamaran type designs there as well. And it worked well, relatively well. 2017, CWind was bought out and taken under control by Global Marine Group, who is a large global shipping company. The cable laying and various big offshore operations. And they were taken under control, and they bought out all the owner skippers. So they controlled everything, and they introduced CWind Taiwan. We had a number of boats working on the offshore wind farms in Taiwan. They introduced a project arm, which was running projects on offshore wind farms, as well as providing crew transfer vessels. And they also started up a training location, training on global wind offshore courses. Shortly after the buyout by Global Marine, we got 4 new CTVs, 23 and 25 meter boats, built by a company called Aluminium, or AMC, and they were aluminium catamarans, which are the general kind of build type of CTVs in Northern Europe. And they were coming in at about 54, 55 gross ton. So slightly, they were bigger, heavier vessels than what was in the business way back at 2010. As part of that development, in October 2020, CWind Pioneer was launched, built at White Shipyard in Cowes in the UK. So it's the vessel itself just over 3 years old now. And then as part of the ongoing development of the company, Global Marine put CWind up for sale 2022. And CWind Taiwan were sold off, and the training company was wound up. And in September 2023, we were bought by a UK investment company called In-Spirit Capital. And at this time, we have 12 CTVs operating. We've sold a couple off, some went to Taiwan. So we're left with 12 CTVs, which are a mixture, 4 aluminium catamarans and CWind Pioneer, and then 6 or 7 GRP catamarans. And that's where the company is now. We've had the investment company has really left the company to run itself. The management team is the same, the boats are the same, the crew are the same. They are having an oversight of how the company's progressing, and I'm sure they will have some input in the coming years. So that's where CWind is now. So let me move on, and we'll talk more about CWind Pioneer. I'm just going to see if I can I move that. Can I move the box down the right hand side, Alan? Let's see. hide thumbnail video. Yeah, that's okay. Okay, so CWind Pioneer, you'll see a photograph there of it there. It is an aluminium catamaran, and it's been designed as a SES, a surface effect ship. 23 meters long, comes in at 52 gross ton, and it's coded, two codes, two UK MCA coding. It's coded on a high-speed offshore craft code, and also the workboat 2 code. And the difference with them two codes, the high-speed offshore craft code allows the vessel, as long as it's been designed, to take more than 12 passengers. And the way it's set up just now, we can take 24 passengers, or the correct description is industrial personnel, because they've been trained in sea survival, they've been trained in firefighting, they've been trained in first aid. They're workers, they're not passengers. And we run with 3 crew. As I said, it's a catamaran surface effect ship. It's got a hybrid system with a diesel, and we've got electrical power supply. And I'll go into a bit of detail on that shortly. And the propulsion is Rolls-Royce water jets, which makes the vessel highly maneuverable. Cruising speed, round about 37, 38 knots. Maximum speed, 45 knots. That's with the hybrid battery boost, and in generally perfect sea conditions. And as you can appreciate, for a 52-ton vessel, 43, 44, 45 knots is quite a substantial speed for that size of vessel. Just a bit of an overview of the main systems, and a diagram there of one side of the system. So we've got 2 main engines, Scania DI16s, producing 850 kilowatts each. And there's a shaft that's then linked directly to the motor generator, and it's a Danfoss, and that in turn provides the electrical power. And then directly linked by a shaft to a gearbox, ZX gearbox, and that in turn is linked directly to our Rolls-Royce Koenigsberg water jets. You'll see then coming off from the motor generator, it goes into our control system, electrical control system, which then manages the power either into the hybrid batteries or into the ESNA equipment. And you can see that the green part is the power, and also it goes back to the motor generator as well, because it's a hybrid system. But I'll talk a wee bit more about that in a few minutes. So that's the kind of quick overview, and obviously I haven't put it on the slide, but it's replicated on the starboard side as well, with the main engine, motor generator, gearbox, water jet, and with one ESNA SES system in the middle. So you can see, and the photograph is of CWind Pioneer from the top of the transition piece on a wind turbine. I'm sure you're probably all aware that ESNA is a Norwegian company providing or producing the surface effect system for small craft, whether it be workboats, military vessels, or whatever. Components of them, and I'm assuming you can see my cursor but there's a lift fan and electric motor. And you can see as you look down the top, that area there is the actual fan, the lift fan, and the motor is on the port side in that area to the side. An electric motor, and as you can imagine, I'm sure you've all got your experience with hovercraft. That fan draws the air in from the atmosphere down, and it drives the air into the hull of the vessel. And I'll show you a bit more of that shortly. Other components for the ride comfort, there's 4 sets of dampers. There's a forward skirt which traps the pressurized air under the hull. There's an aft bag that stops the air from escaping out the stern as the boat moves forward. And there's 2 what's called bag fans, which assists in moving the air from underneath the hull into the aft bag. And I've got some pictures which will hopefully clarify that. So from the left, that's the electric motor, and there's a small shaft there that connects to the bigger shaft into the lift fan itself. And from the same, you can see there from a different angle, the kind of size relative to the life ring. You can see the kind of size that the lift fan is. It's in that area there. Either side of the lift fan, there's 2 sets of dampers, and these are they're fully closed in this picture, and they open sort of to 90 degrees each damper blade, and they're computer controlled, and they're opening and closing depending on the RPM of the lift fan, depending on the sea state. There's pressure sensors in the hull, and depending on the movement of the vessel, these dampers will open automatically and close in an attempt to keep the deck as level as possible. And you'll see I've got some videos later on of the operations that we do on transferring our industrial personnel. A couple of photographs in the next slide. There's a better photograph, but the one on the right, you can see quite clearly the forward skirt, and they are individual skirt lengths, and they're overlapped, and the bottom meter are replaceable so that wear and tear, normal wear and tear over a number of years, then the bottom of the skirts can get replaced if any get damaged or wear out. Obviously, the boat's 2.5 years old now, and we haven't had to replace any as yet. So you can see that the front skirts quite clearly there. If we look at the other, the aft end of the vessel, you can see down here is the bag, sort of the aft bag, and the next picture shows it clearer. So here we go, the right-hand picture. You can see the aft bag hanging down. And if we look at the sketch on the top, I've coloured it in. So the red piece is the bag, and the blue is basically where the bag fans are. There's 2 bag fans that takes the air that's trapped underneath the hull, increases the pressure, and the bag at the back is constantly 10% greater pressure than under the hull, so that when the boat moves forward at speed, then the air under the hull isn't going to escape out the back end, and the air is therefore trapped. And I'm sure we're all aware of the kind of mythology of the surface effect ship, that with that pressure underneath the hull, it lifts the vessel up and minimizes contact resistance in the water, therefore giving us a more efficient propulsion method. It makes it a lot more efficient. So there's two bag fans in the hull, which pressurizes the bag to 10% greater pressure than in the hull. So that's that. And the other part of the picture you can see there is obviously one of the water jets. And I don't know how familiar the audience is with water jets, but generally speaking, the impeller is only turning one way. The impeller in here is only turning one way, producing thrust out of the nozzle. The nozzle, both nozzles on the sets are linked, so that's your normal steering. But to get forward and astern propulsion, the bucket either raises up to allow forward movement, so all the thrust is coming out the nozzle, or the bucket can come down, cover the nozzle, and direct the water underneath the stern of the vessel to give stern propulsion. And each bucket is independently controlled, which there it gives a fantastic level of maneuverability. And that's predominantly a couple of reasons why they've went for water jets in most crew transfer vessels. One is the gearboxes, because when we're going onto a turbine, you know, it's forward back. There's minor adjustments, but with water jets, you're not actually disengaging or engaging the gearbox because the impeller's turning the one way all the time. So there's less trauma to the gearboxes, and because the buckets are independent, we've got a huge amount of maneuverability, and that's why we tend to go for water jets. Okay, let's move on to the next one. From the bridge, the control of the surface effect ESNA equipment. We've basically got two modes: transit mode, which is kind of self-explanatory, and a heave reduction mode. And there is a difference. The heave reduction is designed that we can increase the RPM of the lift fan whilst not making speed. In the transit mode, it's been tweaked so that there's a limited RPM on the lift fan for the given speed that we've got. What we found was that if we had too much lift fan on and not enough forward speed, we were finding the air was migrating outside the vessel underneath the hulls. So ESNA adjusted, and we've got a limited RPM for the speed. So if we're not achieving 15 knots, then we can't increase the lift fan beyond 1100 RPM. And that way it reduces the chances of air escaping out the sides of the vessel. And that was causing some other issues. So transit mode allows, and the other thing is that the dampers that I showed you, the computer system is adjusted slightly differently so that the dampers are working differently as well in transit mode as to heave reduction. So the heave reduction is just there specifically for when the boat's not moving forward. If it is, it might be half a knot and not moving forward. And the aim is to keep the deck as level as possible for us to achieve safe transfer of industrial personnel. At rest, the draft of the vessel is 1.8 meters. At full lift, it lifts up 1.5 meters, and I've got actually 0.3 of a meter in the water, 0.3 of a hull, and depending on the speed, the bag may well be a bit deeper than that, depending on what angle it is. But that's the kind of lift, that's the amount of lift that the lift fan gives the vessel. So you can see how efficient, how more efficient it makes the boat. Okay. Is everybody, can I just check, everybody keeping up? Everybody understanding my accent? Everybody okay?
Yes.
Alan? Yes.
Thank you. Going with you so far.
Good, good, good. Okay, let's move on. Thank you. Okay, so the performance of the vessel. So in transit mode, we'll get 37, 38 knots out of it. And bear in mind, this is in very flat, calm conditions. We can achieve with boost from the hybrid batteries, and I'll talk about that shortly. We can achieve, and we have achieved 45 knots. And the autonomy is, the autonomy compared to other crew transfer vessels is phenomenal. Each engine burning 205 litres an hour, which, as I said, is phenomenal compared to the equivalent crew transfer vessels that they'll be burning 400, 450, 500 litres an hour easily.
Wow.
I've worked on all the types of vessels, and Pioneer is just way ahead of it as far as fuel efficiency and for the speed as well. Them other vessels, which maybe 80 tons, 90 tons, they'll be achieving 23, 25 knots, if that. A significant wave height of 2.5 meters, which is round about 3.3 maximum, 3.5 maximum. Then we'll reduce our speed down to 20, 25 knots, and and reduce it accordingly. It depends on what course we've got and what direction the sea state is in relation to our heading and stuff. One of the incredible things about the SES is that there's a comfort mode, and them dampers, they're adjusting all the time. And the vessel, I've been operating it over 2.5 years now, and it never crashes into any waves. It's almost like it's almost as though you're compressing a shock absorber every time you come down off a wave, and it just gently settles in, and then we're up again, and it's a different ride to a normal catamaran, that's for sure, but it's a less aggressive ride completely. Heave reduction mode, as I said, it's designed for slow speed approach for pushing onto the wind turbines, and it's designed to keep the deck level. And all the movement is taken up automatically by the dampers opening and closing. It's all done automatic. There's not a lot for me to do, or for the crew to do. In the transit mode, just to go back, we've got a level of ride comfort that we can adjust. That means that the dampers are open more, and it's a more cushioned ride. If it's a more cushioned ride, then we will lose some of the speed. We might lose 6 to 10 knots. The more we've got, the more comfort we've got. When it's fully closed, when the dampers are fully closed, and that's when we can reach the maximum speed. Right, so we talked about the engines connected to the motor generator. The motor generators provide the power, and it's from a company called Danfoss. There's a motor generator on each side in direct line with the main engines, and they're producing 130 kilowatts each. They in turn charge or provide the power for the hybrid batteries, and also direct power if we need it to the ESNA equipment. When we go green, it manages the power supply from the hybrid energy storage system, the batteries, to the motor generators, and it optimizes the load on the engines. And we call it a boost, and that gives us the extra 7 or 8 knots at the extra power at the top end of the engine RPM. We can also switch off the diesel engines completely and operate the vessel in electric mode. They decided to call it zero emission mode. So we can just run it on batteries, and we can run it for about an hour, and we can get 6 or 7 knots. And the concept is that we can use electric in the harbour, moving around slowly in the harbour, and we can use it out at the wind farms when we're not moving any teams, we're not moving any personnel, and we might just be waiting for the next task, and we can use zero emission mode. To be honest, we need to be careful when we do use it, especially in harbour, because you haven't got the same type of power. So if we've got 2.5, 3 knots of tide, or any wind over sort of 12 knots of wind, then we tend to be on diesels, so that we've got the power when we want it. Zero emission mode, we can move around, but if we need that additional power for maneuverability, then we could be really embarrassed by it, because it doesn't give us that kind of power. But it works very effectively when it's become a situation. Boom, 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 boom. Okay, so the next system, and you can see that it's a bit of a complex vessel. For such a small vessel, it's quite complex, and it's these different systems getting blended together, which has made it complex. So that the energy storage system is the Corvus Dolphin system, and you can see some pictures there of the cells. So we've got three modules of 5 cells, a total of 15, and they optimize the energy consumption by running the engines at optimal load. So we can, as well as the engines and the motor generators providing power to recharge the batteries can provide power to the propulsion system to reduce the load on the engine and to give us that boost to make the top speed. One of the comments there, state of charge, 20 to 100%. So the batteries, if that's a state of charge, the electrical energy is going to the SES system, and it's going and it's providing an energy back to the motor generators, the boost, when it's over a certain RPM, and it will provide that boost for about 20 minutes, and we can achieve, depending on the circumstances, 38 to 45 knots for about 20 minutes. Then when the batteries reach 20%, state of charge. Then the motor generators then provide the power to recharge the batteries and at the same time provide power for the ESNA equipment. And while it's doing that, the engines are under load. There's less thrust out the back. So we'll reduce speed to about 32, 37 knots during that recharge phase, which takes about 30 to 40 minutes to recharge the batteries back to 100%. And then,
Where's that?
sorry? Trygve, did you say something? No. Zero emission mode, as we mentioned, the energy storage system provides power to the motor generators to drive the propulsion, to drive the water jets without the main engine switched on. Right. Also, another system is it's got its standalone cooling system for the electrical, for the lift fan, for the motor generators, for all the inverters. And it's a glycol cooling system, and there's two sets fed from the same, or the heat exchanger for the cooling system. Each heat is fed from the same seawater intake for the main engine. But it's a glycol. There's two glycol cooling systems. They're pressurized closed systems, which cools all the electrical components. Critical piece of equipment, as you can probably imagine, because with all this electrical going on, the inverters, the motor generators, all produce a lot of heat, and it's a very critical part of the system to keep all that cool. And it also provides some of the cooling system to the inverters in the hybrid system as well. So yeah, so to ensure it all stays at the right temperatures, there's two independent glycol cooling systems. So I think you can see it's just a quick overview. I've got some other photographs of the boat itself, but it's just a quick overview of all the systems of the boat. And I think just that quick overview, you'll probably be going, it's a complex little beast. And with all the different complexities and different companies, sometimes it hasn't been as smooth as it could have been for a number of reasons. But we get there. We've got there in the end, and it's working fine. So what do we actually do then with the boat? I've talked about 24 industrial personnel. So we take them out to the wind farms, and it depends, the wind farms can be either operational, and we're taking teams out there for maintenance purposes, or we're part of the construction phase, and there's other larger vessels building. We're maybe living on service offshore vessels. But generally speaking, on the operation and maintenance, it'll be 12-hour days, starting and return from the base port, and taking technicians out to the turbines to conduct normal maintenance and repair. If it's construction, generally speaking, we'll be accommodated offshore on a large service offshore vessel, and there'll be two 12-hour crews so that the boat's working or available for work 24 hours a day. So that's the kind of concept of where we normally work in. This is during the construction phase. You can see one of the construction vessels, a jack-up with 6 turbines on it, and it's just finished constructing the turbine just off its starboard quarter. And you'll see that the items that are highlighted with the yellow drawings, each turbine has got a boat landing that the boat's designed to go against, and there's polar estuary, there's ladders for the technicians to climb up. There's also a crane davit, electrical, because the turbine's self-sufficient in power. So at that first level, there's a davit to lift all the equipment from the deck of the crew transfer vessel onto the turbine. And on the jack-up vessel itself, there's also a boat landing, because we're taking people from the jack-up ship. Obviously, the jack-up would need to be jacked down to water level to do it, but we're taking people from the ships to the turbines and vice versa, and moving people around the whole construction site. Yeah. Normal, so 24 guys on board, maybe 8 teams of 3, something like that. On the maintenance, sometimes there might be 16 push-ons in a day, because the teams don't need to. The teams will maybe spend all day on the same turbine, or it might be a 10-minute job, and they've got every turbine to do on the wind farm. So some days it may be 60, 70, 80, 100 push-ons to a turbine to get the guys up there, 10 minutes up there, then they come back down. So the day can be very different, and obviously sea state and the environment can be very different as well. Yeah, so that's that. Just some kind of photographs of where we're going. So the right-hand one, it shows you the yellow bit is what we call the transition piece. And in this case, it's got 2 boat landings. That wind farm, there's a 3-knot tide that runs across the ebb tide, and the flood tide is 3 knots. And these ladders, the boat landings, are positioned in such a way to make it as easy as possible with the tide. But there'll be times when you've got 2 knots of tide running across a ladder whilst you try and maneuver the boat onto the ladder. And you can see the top. So the yellow piece is what's called the transition piece. And that platform, there's an electrical davit there. There's an electrical davit there that takes the equipment off the bow of the boat. And if you look on the left-hand photograph looking down on Pioneer, you can see one of the crewmen and a technician ready to go up the ladder. And the boxes on the deck, the boxes and the bags are sort of the level of the equipment, the size of the equipment that each team will maybe take 2 or 3 of them bags or equipment. And they could, depending on what they've got in there, but it varies between sort of maybe 40, 50 kilograms to 300 kilograms, depending on what they're taking up there and what jobs they've got. And that's how, and you can see with a photograph, if you look at the front of the vessel, and each vessel's slightly different. I've got slightly different fendering arrangements to be able to make that connection with the wind turbine. But that photograph there is a good photograph that you can see actually what happens. Cool. Different photographs again. General technicians climbing up, and they're assisted by the crew member. This photograph is not very clear, but every offshore wind farm has got its own power station. Got very different names, but it'll be an offshore substation. So all the power, all the cables will go into the substation. The electrical going-ons will happen, and then from the substation, it's cabled to the shore. And the vessel, or the picture of a crew transfer vessel pushing on a service vessel. You can see, each vessel's got boat landings as well, and that's the kind of routine that we'd be looking at. Couple of pictures of the inside of CWind Pioneer. Bridge, 3 control. We've got the helmsman's position, which is generally the master or the mate. We've got a navigator's position, and to the port side, we've got engineer stroke deckhand's position that monitors, and all 3 positions can monitor the systems, but only 2 of them has got navigational equipment in it. Down below, you'll see the right-hand picture. There's a kind of seating arrangement for the packs for the technicians, and that's kind of laid out. And small galley area at the back, and a small sort of tool storage area at the back as well. To finish off, got 2 short videos to show the kind of thing that happens. This one is not from the CWind Pioneer, but it's from another CWind vessel, and it's a kind of normal day. You see the deckhand pulling down the fall arrest equipment. The technician clicks on, and it's always the technician's decision whether he considers it safe to go. The master's decision first of all, and then the technician, he makes his decision whether it's good enough to go. But there's very little movement there. And that's safe, normal transfer. I'll just show you the next one. Okay, this one it's a video of a video. You can see the CTV, and to be honest, we don't take a lot of videos of it, but I thought we would take. So this is CWind Pioneer, and it's a recording of the CCTV for a certain turbine, and I'll start it. And this is a kind of normal day, to be honest. And if we concentrate on the bottom left, and there's a bit of boat movement. We're not on the turbine yet, and we just take a bit of time to manoeuvre the vessel and get it positioned correctly. And this is where the manoeuvrability of the water jets come in. You've got very minimum controls, very accurate. Hopefully. And you can just see eventually, or what was the other one? You'll see on this video that it's just precise control, and then the last 6 inches, 4 inches, you just make nice close contact and nice gentle contact. much the kind of same thing.
Ian, it's Alan here.
Yeah.
Whilst you're showing that, you're showing the approach to the wind turbine itself. But
Yeah.
what's the tech? I'm not clear about the technique you actually use to actually lock on, if you see what I mean.
Yeah, there's no lot. It is friction. It's friction between the fender and the turbine, and it's all about power. The power that you're producing at the aft end, whether
Okay.
it be water jets or props or whatever.
What I was thinking of was, do you aim to make the physical connection when the bow is going up or down, or you aim in the middle, or
it's kind of the bottom of the trough or the top of the waves, either one, and it's just where you're at in the wave process. But yeah, certainly it's just the technique is you just hold it 2 or 3 inches away, and then when you can, and normally I think most of us probably do it at the bottom of the trough, and as you're down, that final push on over the 2 or 3 inches, you just creep ahead and do it at the bottom of the trough, and then once you've made that contact, you put the pressure on. And what we tend to do is we might only put half power on, so that with the rubber on the fender dries and warms, and the actual tube itself gets dry, and then we'd put maybe 60-70% power on to stick. And one of the things about Pioneer, I've been doing the job 14-15 years, and even for a light boat, it's probably one of the best boats at sticking on and not moving. I say we work out there daily on 2 meter wave height, significant, and Pioneer doesn't move. And there's a couple of reasons for that. We think, myself and my back-to-back master, we came to the same conclusion separately. And what we tend to do is we take the lift fan off, so the boat sits down in displacement mode, and the bag at the back fills with water. Okay, so it can flow out, but that amount of weight just stops the whole pendulum motion. And also, the water jets are deeper. The water jets are 2 meters deep in the water, and we're getting undisturbed water through the jets, and even in all the through transfer vessels with water jets, it's known throughout, the deeper the water jet, the better thrust, the better friction we've got when we're pushed on. So we tend to, that last half meter, we generally switched off the surface effect part. We've turned it, we've lowered the RPM, the boat's sitting heavy, and then we push in and we get that last bit done. And then the boat doesn't move. It's amazing. It's really good. Anyway, gentlemen, any other questions? I've probably waffled on for a good hour. I do apologise. If anybody's got any other questions, then please fire away.
I was wondering, I'm definitely non-technical, but I was wondering if your skirts are made of neoprene still. My contact with the business is many years ago working for a firm called Hover Marine, which looks quite familiar. Some of your vessel, I don't know if you know anything about Hover Marine, but are the skirts neoprene? Because that was used to be one of the maintenance issues that we had in those days.
They're not neoprene. They're really heavy, quite heavy grade rubber, and I'm sure they must be. Say I don't get to see them much. We don't take the boat out of the water that much, but they're really heavy grade rubber. I would, my memory, probably 10mm thick rubber, and they may well be impregnated with something to give them a bit more strength. But no, they weren't. They were kind of well thick, flexible rubber.
Ian, I think near Skormedal could probably help us here for
Yeah,
Roderick
sure.
as well.
Hello, everybody. Can you hear me?
Yes.
Yeah,
Yes.
we can hear you.
Good. Yes, talking about rubber skirts. I think the bow skirts is made of I think a combination. Some part is neoprene or natural rubber. It depends, but it's kind of reinforced by nylon, and it's about 3mm thick, I think.
Yeah.
Yeah, but the wear on the CWind Pioneer, because we're running at quite low cushion pressure, so really the flagellation loads and wear rate of the skirts are less than we anticipated even.
No, that's good to hear, really.
Good. Thank you.
But, yeah. Is that what you wanted to find out, Roderick, or? Is there more?
Yes, it was just a matter of interest. I used to negotiate with the providers of those things, and since the temperatures when you were running at speed would often get up to several hundred degrees Fahrenheit, the wear used to be 40 years ago fairly significant. My guess is the materials have improved a lot now.
Yeah, and also there is an option that we can replace the tips of the fingers. So and it's quite easy to change the skirts when you are in water. But I don't think they have done it yet on the CWind Pioneer.
No, we haven't had to do it. You know, we inspect them. We inspect them monthly in the water, and we've never, as I say, we haven't changed any of them yet. We haven't really noticed any wear and tear at all.
Well, good luck to you.
Yeah,
I'm happy to see another surface effect ship back in operation again.
it's interesting, actually, Ian. Well, probably John could tell us a bit more, but with the amphibious hovercraft, I think they've generally found, because the wear rate is a bit different, that there it's easier to simply replace a complete segment rather than try repairing it. I think that's fair, isn't it, John?
Yeah, I think generally there's some operators will put new tips on, but generally it is the whole. The segment's much smaller than that very deep segment that's on that craft. Yeah. Sorry, I'd just like to say that's a very interesting talk, and I think it's an excellent use of an ACV in that situation. I think it's very, very interesting. Would just like to ask the question that the making it putting in the battery backup and the electric generation and recovery, does it give you the benefit that the added complication would seem to be in something that's working on a marine environment all the time? But I don't know if you're just interested in any comments.
Yeah, obviously it makes it a lot more complex, but and we've discussed it, and the only obvious thing then you would still need a power source for the lift fan,
Yes.
whether
Yes.
electrical or diesel. You know, I know that the other SES boats that are within the wind farm industry have got diesel engines to provide power to turn the lift fans. So, you know, would you lose the efficiency there, or, you know, the added weight of another engine, or if it was 2 lift fans, two smaller engines to power them? But yeah, because we've often sat down and thought, what if we didn't have the hybrid and we just had another power source, a power source for the lift fan? Would that have been more efficient? And yeah, I don't know if we're in the right people to be able to say yes or no, to be honest.
Well, I think we do have the right people here, I think, Iain,
Yeah.
particularly with Near and people like John, who's been in the business a very long time. But my comment and perhaps question is that hybrid system, is that impacting on your, if you like, support manpower within CWind for the boat?
Well,
or is it simply an operational complexity?
it's an operational complexity.
Okay.
I would have liked to have said that we had no problem, and we haven't really had any issues with the Corvus equipment.
Okay.
We unfortunately we did, but that was because we got water in the compartment. Unfortunately, the design of the boat and the space, the battery space is below deck with flush deck hatches, and no matter how good you think flush deck hatches are, they always leak.
Yes.
So
Okay.
you know,
Yeah.
we had the batteries inspected, and they showed signs of saltwater ingress or saltwater contamination. And with lithium-ion batteries, that's the last thing you want. So we ended up getting a set of batteries condemned because they showed evidence of salt water. But they were working fine, you know. They were,
Yeah.
you know, we didn't, when we still haven't had any issues with the Corvus systems. It was unfortunate that some other systems failed, and we had to get them batteries swapped out. Yeah, but you know, they work fine, and the system, you know, once it's all in and we know how to manage it as a crew and monitor it's, you know, we need to monitor them very, very closely, but they've got a management system in there as well. Yeah, so in case something does go wrong, we're warned as early as we can that something's not quite right.
Okay. Just out of interest, did you actually change the hatches to improve the water?
They're actually getting done now.
Okay.
Yeah, there was 2 issues. One, yeah, the flush deck hatches, which was raised way back in the early days, and here's one for you, like the bilge output. So it was either the bilge output, because of the speed of the boat and the water pressure, and the different movement, but the non-return valve put in the pipe work for the bilge pump before it exited the boat was put on a vertical pipe. So there was no U-bend in it, there was no water trap. It's just a straight vertical pipe and then out. And we think because of the movement of the boat, which is very up and down, that perhaps we know we got a lot of water past the non-return valve on the bilge outlet, because it was put vertical. It was built in a vertical pipe. We've subsequently changed and put a bend in the pipe so that the non-return valve is in a horizontal piece of pipe, and that seems to have solved it. You know, so it's we've learned, if we ever do a next one, we've learned an awful lot of bits and pieces that we will certainly feed back during the build phase. You know, but there we go. Just simple things, really.
Yeah, it's the typical issues that happen with a prototype. I would say it's tend to be very small things, but it can be important.
Yeah, but, and it can have an impact 12 months down the line. You know, simple things. But all in all, it's we're getting there. We're getting there. It's actually back in the shipyard this week, getting lifted out and sort of having its annual surveys, bottom scrubbed, water jets checked and everything. So yeah, it's out of the water at the moment, down in Cowes. So it'll be interesting to see its performance when it goes back in the water with a clean bottom and everything tightened up, you know.
Yeah. Okay,
So
gentlemen.
it's come back to the Isle of Wight then, has it?
It has, yeah. It's in White Shipyard just now.
Yeah. So where's it been operating? Sorry, I missed the right at the beginning of the talk.
Oh, sorry, I didn't mention actually. Sorry, it's initially we took it over to Vlissingen in Holland, and we were working out there for 9 months with Ørsted, which is a wind farm operator, and then it got moved over. It got moved over to we're working out of Ramsgate on the East Coast, Kent, working for a wind farm operator, Vattenfall, and they're very, very happy with it. It's we've had issues with it, but every CTV there's issues, but yeah, they're very, very happy with it, with the performance, and the fact that we can work in the top end of the operating range, and the technicians are happy with it, transferring. It gives everybody a level of security, knowing that the boat's not moving, and they're very happy with it, yeah. And the fuel efficiency as well, they're over the moon with. But yeah,
I should think that's playing. I mean, but as the whole thing comes to more and more wind generators being used, the fuel they use is going to get more and more. The fuel that support vessels are using are going to get more and more critical, I'd have thought, or more and more important.
And it's being looked at more. 10 years ago, 5 years ago, it was just a cost. You know, it was a cost that everybody accepted. But now the operators are really, when they're doing the contract tenders, you know, they're looking at the efficiency of the vessels completely. Yeah.
Thank you.
Yeah, just to comment on your question, John, also for Iain, up here in Norway, during March, the tenders for another offshore wind area, this time in Norway, southern North Sea area, for 1.5 gigawatts of new projects that will be awarded later this year. The tenders are on at the moment. The decisions are being made at the end of March, and then we'll go into the award phase and the development. Of course, there's up to 30 gigawatts being developed around Scotland at the moment.
Yes,
so
there is. Yeah.
The number of projects, well, I don't know how many projects it is, Iain. It must be, I don't know, somewhere between 10 and 20. But and each of those require almost a fleet of vessels to construct and eventually maintain them. So this is very, very big business coming up. The squeeze is going to be on delivery of such vessels.
Yeah, and there's more and more CTV operators are gone down the hybrid route. Windcat has gone down hydrogen route, and there's a couple of other SAS vessels, isn't there? Yeah, so everybody's trying different ways to make the whole operation more efficient.
Yeah, but yes, of course, UMO have delivered 2 further craft to Great Yarmouth in this last year. So there's 4 SES operating out of there for the moment, and I'm hoping a little later on in the year that we might be able to get a talk from them. But they're settling down to new ownership at the moment for the operation. So yeah. Okay. Any more questions or comments from anybody?
Ian, it's Chris Fitzgerald. I found it a very fine presentation, and thanks for the effort you've made to give us this information. You did mention at the early part of your talk about cushion stability or air escaping along the sidewalls. I wondered if you could explain what the result of that is, or are there any dynamic issues when you're traveling? Do you get roll, or like a Dutch roll, or any strange cushion effects?
No, what we were getting originally, because we were new, what we were finding that if we increased the lift, therefore the pressure under the hull, and the boat wasn't moving forward sufficiently, we were getting a lot of the air migration out from the sides, and it wouldn't have been an issue if it hadn't been for the saltwater intakes, the engine, because everything runs from one sea chest. So the engines were man enough to, if we were getting air migrating into the sea chest, and the engine water pump impellers were man enough to get through it, just running dry for half a second and a half. They were man enough to get through it and draw water. It was all the various other pumps, smaller pumps, that were feeding from the same sea chest that were failing, because we were getting air in the sea chest, and it created quite a large problem for us at the time. And again, well, we solved it through ISNA and putting in a limiter for the amount of lift we could generate for the speed, and we also solved it by putting non-return valves in the pipework between the sea chest and some of the smaller water pumps that were drawn from the same place. So that was the main issue, was my air migrating into the sea chest and burning out water impeller pumps.
It's interesting what you say, Ian, there for Chris as well, that the impression I get is that actually the cushion system for this SES is well, I'd say over-designed, but I don't mean it really that way. But it just has the capability to literally lift the boat out of the water, if you see what I mean. It's not literally coming out, because there's always got to be some displacement. But it's a very high flow system capability.
Yeah, and very efficient, and the boat was built. They constructed it with the final weight being critical, and it makes the boat quite lightweight, and quite you know, people would look at it and go, oh, really? Is it man enough to do the job? Because it's been built to the minimum weight limits that they could, you know. So yeah, the lift fan just lifts it. You know, it's a very, very efficient system, and it just lifts the whole boat out of the water with very, you know, with maybe only using 2/3 of the power available. The whole boat's out of the water.
Sorry.
Maybe I
Neil.
can comment a little bit.
Absolutely.
Yeah. What is different from this vessel to others is that we have just one lift fan. And we have a very big lift fan, very high low flow velocities, very high efficiency, above 80%. And it's very forward. So and it makes also very little noise. So the main engines is the main source of noise to the passenger compartment. But I would say that we had this problem with the air suction to the cooling system at speeds below hump, and we agreed just to put a kind of speed limit, a cushion pressure limit on at low speeds just to avoid that. But at full speed, in highways, I still feel that we have not sufficient air. So I would want to have even more air to be able to control the motions more sufficiently. But that is a compromise we have to do in the design process of such a vessels that in high waves we could, at high speed, we could maybe have needed more air. But yeah, Iain.
Yep.
Thank you very much for a very good presentation, and I really liked it.
Good. No
I
problem.
think you are doing a tremendous job out there.
We're doing our best.
Mastering such a complex vessel.
Yeah.
It's remarkable what you are doing.
It brings operational difficulties with crewing and training. You know, within the CTV world, the crew are very movable, and our biggest problem is keeping our crew and keeping the guys that are familiar with the boat, and then, you know, trying to keep them on it without them being going somewhere else. And then we need to start the whole training process again. And it's not so much the training, it's just the familiarity of it, because it is quite complex. Yeah.
In that respect, Iain, I noticed in the last month, of course, or rather CWind is recruiting, and one of the points they were making is that the contracts available to the staff is more than a year. So I assume from that most operators don't offer long or permanent contracts. Is that true?
I would probably say 65 to 70% of their crew are on long-term contracts.
Okay, all right.
Yeah, throughout the industry, and then there's always a group of freelancers that are quite happy just moving around, and that suits the operators as well, because generally speaking, during the winter months, there's maybe a 15-20% slowdown over the winter months. So the freelancers don't use. But yeah, this time of year, there's always a bit of a rush on to get people on boats. But it's changed over the last 4 or 5 years. The boats have been the CTVs have been getting bigger, heavier, more capable of working through the winter. So, you know, most of the CTV operators are keeping their crew on long-term contracts. Yeah.
Yeah. Oh, okay. Understood. It's very important for the training. And as the projects move north, whether it be to Scotland or north of Scotland, or even here in Norway, on average, the weather is going to get more challenging throughout the year. So that's going to put a pressure on training and so on.
Yeah. Yeah.
Okay. Any more, or shall I bring it to a close now?
Yeah, Alan, I'd
Yeah.
like to ask Ian a question about the louvers that you showed us a picture of them, where the exhaust air is allowed to escape from the bow, but I couldn't quite understand exactly where they were. Are they close to the lift fan intakes?
Yes, they are. They're positioned two of them on each side of the lift fan intake. Yeah. So straight adjacent to the lift fan, both sides. So that the air's funneled back out either side of the lift fan.
Yeah.
Yeah.
So
electrical actuators that opens and closes them.
Yeah. So are those actuators activated by the motion of the vessel, or are they cushion pressure?
Cushion pressure. I think there's, off the top of my head, there's 6 pressure monitors under the hull, and they in turn send the signal to the computer box, and the brain then activates the dampers.
Yeah.
As I said, on the transit mode, we can adjust them manually, electrically from the operator's position.
Yeah.
So you've got a -5 ride comfort, which is them fully closed, and a +5, which cracks them open to about 20% off the top of my head, which creates more bounce, more sponge effect, and it reduces the boat in the water slightly, which slows it down. But the ride is substantially different if you've got it in +5 or -5. The difference is quite formidable. Yeah.
So these vanes are not in the fan discharge, they're in the cushion, so they exhaust the cushion to atmosphere.
That's correct.
Yeah.
Yes. Yeah. They exhaust the hull, the cushion to atmosphere. Yeah. The intake fan is a sealed compartment, really.
All right.
From where the air goes into the fan to where it enters in underneath the hull. Yeah.
It would be, obviously, from an energy point of view, better to throttle the fan and reduce the amount of power that's used and the amount of air that goes in, but I guess that's a very complex thing to do.
Well, on the heave reduction mode, it does it slightly. It reduces it because there's a louver effect after the fan before it gets into the hull.
Oh, really?
Yeah, and then the heave reduction mode, that closes by 10%.
Oh, brilliant! Yeah.
So that reduces the airflow in, and that's something that ESNA set up. It's nothing that we've got control over. It's set up with a system.
Yeah. Well, that's interesting. I'm wondering when people are going to do that in the amphibious hovercraft world, but
yeah, I don't know enough about that. Sorry.
Thank you.
No problem.
I can add that ESNA, we are the designers behind the vessel, but we also have delivered the SES systems, the fans, which are not our design, but we have specified them, and they are built in UK, the lift fans. But all the dampers and the control system computers are programmed and coded by us. So this is equipment package we can deliver to any yard in UK or wherever, so that any yard can build an SES based on our design, because we supply them equipment which you can't buy actually.
Yeah, the proprietary delivery from Esna.
The complementary equipment together with the design.
Seaman, Morten, or Stig, do you have any queries?
Oh, thank you, Ian. It was a very thorough and good walkthrough of the vessel and your operation.
Hi, Martin. Hi.
Hi.
Thank you.
Seaman? Or Stig? You're both muted, that's the problem.
Yeah.
Oh, well, okay.
Okay.
Don't worry. Yeah. Okay, then I think it is time to bring this evening to a close. And gentlemen,
Can I ask a question?
Oh,
Yes,
no, please. Sorry, sorry.
Ian, is it possible to have a copy of your presentation?
Yeah, not a problem. Yeah.
Yeah, if you can, yeah, maybe Alan can give you the email address if you don't. Maybe you have it.
It's all right. I'll arrange the
no
link
problem.
near. So
Very
yeah,
nice. Very nice to have it.
Yeah.
Thank you very much.
No problem.
And John, it's nice to see you. A long time.
Thank you, Ian.
Yeah, and yeah, the feeling's mutual.
I hope we can have more meetings like this. That would be very good. Okay. All right then, gentlemen. I will thank everybody for your contributions tonight. I hope it's been an interesting presentation and also discussion. And we'll put that online in a few days' time. Yeah. Thank you very much, everybody, and look forward to meeting you at the next presentation, perhaps. And Ian, a very special thank you to you. And I guess on behalf of everybody, I wish you a very successful operating year this year once the vessel gets back in service.
Yeah. Okay. Thank you very much. No problem.
Yeah.
Thank you.
Thank
Good
you.
night, everyone.
Yeah. All right.
Thank you. Good night.
Good night.
Good night.
Yeah, right.